Now, whenever you have a complex forming, the chances of isomers being formed, and the isomers exactly the same way as organic chemistry. Number one that we're going to discuss, they called geometric isomers. Now, in geometric isomers, in organic chemistry, if you remember organic chemistry, isomerism is due to different orientation of bonds. So in organic chemistry, you had in geometric isomers, you had the cis and the trans version of a particular molecule. So you had cis and trans isomers in organic chemistry. Now they're going to be very similar. The concept would be very similar, but they're not going to be exactly the same thing. In organic chemistry, you had a molecule and carbon, a double bond was must, and the molecule had two different groups attached on either side. The carbon in each of the double bonds, they would be bonded to two different groups. So there would be two versions of the molecule. One of them would have one side would be switched. The directions would be switched. So the Cl, which is pointing downwards, would then be pointing upwards instead over here. So the bond is still with the same carbon atom, but the direction of the bonds is different. So you switch sides, and this one is going to be called your uh, trans isomer. Why? Because you have these hydrogens and they're pointing in the same direction. Over here, you have these hydrogens and they are pointing in different directions. So this one is going to be your cis version of the molecule because they lie on the same side, and this one is going to be the trans version of the molecule because the same type of groups are lying on opposite sides. So this was the concept of cis and trans isomers when we were talking about organic. When we talk about optical isomers, now optical isomers are not exactly the same thing; they're different. So I'm going to show you one cis and trans version, one geometric isomer first. And this would be, I'm going to take the example of, you could get any molecule, but the concept would be exactly the same. And we're dealing with octahedral complex initially. So we're talking about octahedral complexes and geometric isomers in those octahedral complexes. Remember, we have all sorts of complexes with all sorts of different shapes. So geometrical isomers, we'll be talking about it, and the molecule that I'm going to give it as an example is this one. There's copper bonded to NH3s, four of them, and there are two water molecules, and the entire thing has a charge of it has a charge of two positive. So I'm going to quickly try and draw this octahedral complex, and I'm going to show you the cis and trans version of the molecule. So starting with copper, copper would be somewhere in the middle. It's going to be 2 plus, and it has a total of six sides around it. So there would be six sides around it. There's going to be so there's one bond coming towards you. These are your x, y, and z axis. So six x, y, and z axis, and you have a total of how many NH3s? You have a total of four NH3s. So the four NH3s would be attracted to it, and they would be bonded to it. So these are your four NH3 ligands. The lone pair is getting attracted to the copper 2 plus. And there would be two water molecules, and the two water molecules, there's only z axis left. So the two water molecules are going to be opposite to each other. Now, this version of the complex ion would be known as the trans version. This is the trans version of the complex ion. Why? Because water molecules are 180 degrees apart. I mean, they're exactly on opposite sides. There's a water molecule on top of copper 2 plus. There's a water molecule at the bottom of 2 plus, copper 2 plus. It could have been 90 degrees apart. The other water molecule could have been on any other axis, but in this version, the water molecule is exactly on the opposite side. So this one is your transversion of the molecule. So I'm going to draw the other version now, which is going to be the cis version of the molecule. So again, you have copper 2 plus in the middle, and this is my z-axis, and this is my x-axis, and my y-axis. Now, this one, the other version would be that the two water molecules are not 180 degrees apart. You still have two water molecules, but the orientation would be different. So there's a water molecule over here, and there's going to be another water molecule which would be over here. So there would be two water molecules, but this time one is on the z-axis, the other one is, let's call this the x-axis. So the other one is only, they only have a 90-degree angle between them. So it's so basically you can consider them as being on the same side. And the rest of the NH3 molecules, they're going to have, there's going to be an NH3 over here, and there's going to be another NH3 over here, and there's another NH3, and a fourth NH3 on this side. So this one is my cis version of the molecule. So this is going to be the cis isomer. The water molecules are 180 degrees apart. So the other, so these are the only two possible. Okay? The other ones would just be rotated versions of the same thing. Now we're going to discuss another octahedral complex, which would be very similar to this one. And in this octahedral complex, you have instead of four. So one thing that you have to keep in mind is that a cis and transversion would exist if there are four NH3s or any ligand. It doesn't really matter NH3. If you have two different types of ligands, four are of the same type and two are of a different type. But then there's going to be another cis and transversion that's possible if the molecule had this formula, the complex ion had this formula that there would be three NH3s and three water molecules. Now, in this case as well, there's a possibility of isomers forming. If there are three NH3s and three water molecules, to be precise, there should be three. So I'm going to draw two versions of the molecule. So there's copper 2 plus in the middle. So let's draw both of them together. So this is copper 2 plus right in the middle. And you have the axis, which are so here are all your axes. Copper 2 plus. Now three NH3s and three water molecules. Now one of the example would be that the water molecules are 180 degrees apart. So you have two water molecules that are 180 degrees apart, bringing in and sticking around with their lone pairs. And the NH3s are also I mean, two of the NH3s at least are 180 degrees apart. And let's change the color of one of the complexes. And you're going to have, now you're left with one NH3, so you have to bring that NH3 in. And you have to bring in a water molecule, the third one, which would be over here. Now, the basic idea is at least two of the water molecules are 180 degrees apart, and two of the NH3 molecules are 180 degrees apart. So we can write that down, that at least two water molecules are 180 degrees apart, and two NH3s are 180 degrees apart. Now this one is going to be called your transversion of the complex ion. So that's your transversion. And there's going to be another version where they're not 180 degrees apart. So you have a water over here. The other water is 90 degrees to its on another axis, and the other one is the third one is 180 degrees up on the other axis. Now look at the three water molecules, the x and the y and the z axis. They're all orthogonal to each other. They're 180 degrees apart, and they're not making a 90-degree bond. And the NH3s, I mean, they're making a 90 degrees a bond, but they're not 180 degrees apart. And the NH3s would be the same. So there's an NH3 on one of the axes, there's an NH3 on another axis, and there's an NH3 on another axis. So you have these three NH3s. So I'm going to write this down, that all water molecules are 90 degrees to each other. And also all NH3 molecules are 90 degrees to each other. So these are two, this one is your cis version because they're on the same side. So one of them is a transversion if they are 180 degrees apart, and the other one is going to be your cis version. So you have, so you're going to have isomers, and ignore, I mean, what I'm basically talking about is an octahedral complex which has four ligands of one type and two ligands of another type. That's when isomers would be formed. If it was 5 and 1, then it wouldn't be I mean, no isomerism would be possible. If five ligands are of the same type and there's one ligand of a different type, then there are no different versions or isomers of the same. There wouldn't be any variation in the three-dimensional orientation. And the other isomer that's possible is if the combination is 3-3. If there are three NH3s of one type, three ligands of one type and three ligands of another type, even then, there are two possible sets of orientations that are possible. So now we're going to move to the next version. Remember that cis and trans. I mean, you have. So moving to the next one, which is these complexes, they can have many different shapes. Okay? Octahedral is just one of them if you have six ligands. But previously, we've already discussed the shapes could be, you could have many different shapes. For example, there was a tetrahedral shape somewhere. Just one second, let me find this out. Okay, so if you had bigger ligands, you had tetrahedral arrangements. Now, remember, in tetrahedral arrangements, cis and trans isomers are not possible because they're not two sets of angles. There's all angles are 109.5 degrees. So even if there are two sets of ligands, no matter which way you arrange them, the angle between them is always going to be 109.5. It's not going to change. Just now, octahedral kenda, you had two sets of angles. They could be 180 degrees apart, they could be 90 degrees apart. But that's not a possibility over here. So tetrahedral complexes, they always have they don't show stereoisomerism. They can only show stereoisomerism if they become chiral. But that's not a possibility because for chirality you need four different sets of ligands. Uh, Usually that's not a possibility. I mean, you have a metal ion in the middle. Any solution doesn't really have four ligands, so that's going to be very rare. I mean, it's a possibility, mirror images, and they can form optical isomers like chiral centers in organic chemistry, but that's not really possible to have four different sets of ligands. I say, anyways, we can move. We can talk about cis trans for now, geometric isomers. So remember, geometric isomers are possible in this shape. They're not possible, or they're not possible in in a tetrahedral arrangement because it's in a tetrahedral arrangement. It's geometric is not possible. Again, specifically, what I'm talking about is geometric isomers. We haven't touched optical isomers yet. So this is only limited to geometric isomers. All angles in tetrahedral are 180 degrees. Similarly, it's not possible in any other shape like linear. I mean, all angles are 180 degrees. So, I mean, there's linear is not going to have any variation. Or you could have a trigonal planar arrangement. Now, in that case as well, all angles are 120 degrees. Like if I have a trigonal planar complex, let's assume there's this random complex with an X metal ion bonded to three ligands. Let's call them Y with lone pairs coming in, and there's another ligand with Z with lone pairs. Now, no matter what you do, whatever position you put them in, that I mean, it's not going to. Even if you switch any of the ligands, it's going to be a rotated version of the same thing. Like if I get the Y on that side and the Z on this side, it's pretty much going to be the same exact arrangement. They still have 120 degrees. It's just a twisted or a rotated version of the original molecule. So they're not going to show any type of isomerism. Now the only other possibility is square planar. So we're going to talk about geometric isomerism in square planar complexes. Now, square planar is just a derivative shape of octahedral. Like square planar is when you don't have a ligand at the top and at the bottom. That's square planar. X-axis, y-axis. So when a ligand is making four bonds, that's square planar. So geometric isomers. Now, geometric isomers, and there's one that you need to remember, and that one is cisplatin, and there's another one which is transplatin. And I'm going to write what platin is. Now, platin is basically it's platinum with two Cl ions and two ammonia ligands. The overall charge is zero. Uh, the complex is like this. There's platinum with 2 plus in the middle. All the ligands are all the ligands around it. So all the ligands around it are have 90 degrees angle, so it's they're all 90 degrees to each other, and they're all lying in the same plane, which is why they're planar. So there could be two arrangements. One is that the Cl minus one ions could be next to each other, and the NH3 could be next to each other. Now this one is your cis version because they're all the same side. They're all 90 degrees to each other. The other one is transplatin. Transplatin would be that again you have platinum 2 plus and it has four sides. So it has four sides and you have Cl minus 1, but now the Cl minus 1s are on opposite sides. And you have NH3s and the NH3s are also on opposite sides. So they're all on opposite sides now. Now it's going to be called a transversion of the molecule. So this is your transversion because they are on opposite sides. And the angles now are 180 degrees. So they're very similar. They have exactly the same formula, except for the fact that over here the NH3s are pointing in the same direction, or they're roughly 90 degrees apart. Over here the NH3s are 180 degrees apart. अच्छा उसके बाद roughly ये कि this is just to give you an idea of cis and trans isomerism in complexes. You're probably going to just meet them in square planar arrangements or in octahedral arrangements. But this is just one example. There could be many examples, and you should be able to uh, figure out whether arrangements are possible or not possible. So, for example, if I give you a molecule and I tell you that, let's say there's a molecule of nickel attached to a bidentate ligand, and also attached to two water molecules. Now, this is, and the whole thing has a charge of 2 plus. So this is one complex. Now you should now you have given you the general idea of what a cis and trans isomeric arrangement is. You should be able to figure out how this molecule is attached to two. I mean, you can draw the first version, and I'm telling you that I've already given you the information that it's an octahedral complex. So there's nickel in the middle, and you have okay. So you have these. So you have these six sides. Now, one version would be that since it's a bidentate ligand, it has NH2 coming in, NH2 coming in from the other side, and the two sides are connected. It's a bidentate ligand. It's connected with CH2. So that's a bidentate ligand getting attached, and there's a bidentate ligand on this side as well. Actually, there's another there's another CH2 getting attached, and there's going to be a water molecule at the top and at the bottom. So this one would be the transversion. Why? Because the water molecules are making an angle of they're making an angle of 180 degrees. And you can obviously make another version of this molecule, uh, which is going to be where the water molecules would be next to each other. We can draw that quickly. Just 1 second. So again, there's nickel, and you have so there's nickel, and इसको close कर दे. So the other version would be that the water molecules are next to each other. and there's NH2 and CH2, and the bidentate ligand is attached someplace else. And there's a bidentate ligand attached. I mean, they're next to each other now. So that's going to be your cis version. Why? Because the water molecules are have an angle of 90 degrees. So these are the two. So you could be given any question about this cis and trans arrangement. Remember this, that it only happens in octahedral complexes and square planar complexes. Otherwise, it's usually not happening.